right? Okay, so, oops, that's, how is that? Better? Okay, so how is it related to the electronic structure and nuclear problem that we discussed in Born-Oppenheimer separation just a lecture ago? So the relation is the following. We have the total problem, right? So we split it to the electronic one, solve the electronic one first, according to Born and Oppenheimer, right? And then the Born-Oppenheimer suggests that we write down the total wave function as now as a product. And after integrating out the electronic part, since we solve it with a fixed nuclear configuration, we are left with the question: what is the nuclear wave function doing? Okay. So this nuclear wave function is in Born-Oppenheimer approximation given by this equation, right? So it's kinetic energy of the nuclei and the potential of electrons, right? So when we were talking about like hydrogen, these potential energy surfaces look like this. And for other molecules, diatomic molecules, they look like this. It's, by the way, ground state only. So the excited states are maybe, they could look dissociating rather than stable, like in the case of ground state, right? So keep that in mind. So there are multiple solutions for the electronic problem. And all these solutions, they go here in the nuclear part and define the different nuclear eigenstates. Okay, so for every electronic solution, we will see that there will be multiple nuclear solutions that those correspond to a different levels, right? So before electronic Schrödinger equation, the one that we formulated for electrons, it had eigenvalue problem form, but the eigenvalues, they were parametrically dependent on nuclear coordinates, right? And there were multiple of them, and the electronic functions also had parametric dependence on nuclear coordinates. So when we fixed on a particular electronic state, then we can look at multiple nuclear wave functions that will essentially experience the electronic cloud, right? So the same electronic solution. And that's the idea, that every electronic wave function has corresponding electronic energy. Electronic energy creates the potential for the nuclei, and the nuclei, they sort of behave again as quantum particles. And we will be solving, in this case, equation 7 with some approximations to get an idea how the nuclear eigenstates in the, say, diatomic molecule, how do they behave, right? So that's the idea. So how do we get to the simple enough equation? Because so far, what this equation 7 is some arbitrary function of electronic energy with respect to coordinates, right? And this arbitrary function is, well, it's going to be difficult to solve, right? So in general, the kinetic energy is a second derivative operator. This function of electronic potential is some arbitrary function. So yeah, it's a difficult problem. Now, to simplify it, what we do the Taylor series expansion. Why do we do Taylor series expansion? Well, because Taylor series expansion for any function that you want represents function as polynomials, and polynomials are the simplest functions out there to deal with. So we do Taylor series expansion of the electronic energy. We get a particular value of energy as a constant term and so on, right? So we can choose this R0 point to be a point of the minimal energy on the electronic side, right? Minimal ground state energy configuration. And then because it's a minimum point means what does it mean for the derivatives? So what is the value of the energy derivative with respect to nuclear coordinates in the minimum here? Does anybody pay attention? Basic calculus. So how do we find minimum or maximum? What is the condition? That's opportunity to show that you know calculus. Yes. Second derivative is 0. No, that's not the minimum, right? Let's think a little bit. So what is the physical meaning of derivative or geometrical meaning of the derivative of the function? Slope. Remember that? What they were teaching you in calculus, like whatever function, let's say parabola, and then what's the derivative? Derivative is the value of the well, it's a slope, right? So coefficient to every point. What's the coefficient of that linear what's that linear graph, right? So, and what's the coefficient for the minimum or for the, let's say, maximum? It is 0, right? So, but it's a first derivative, right? So not second. And while once you mention the second derivative, let's talk about minimum versus maximum. What's the difference between minimum, maximum? Can we find the difference between minimum, maximum using just the first derivative? Yeah, there will be 0, exactly. So how do we figure out whether what we found, if you were looking for 0 first derivative, how do we find whether what we found is a maximum or minimum using second derivative? Yeah, what's the procedure? All right. So the magic of the second derivative is very simple. So if it's positive, then it's minimum. If it's negative, then it's maximum. The easy mnemonic rule, how to remember positive, negative, minimum, maximum is the following. If you can pour, imagine this is a glass, right? If you can pour water in it, then it's positive. Okay? So that corresponds to the minimum. If you cannot pour water in it, then it's negative and it corresponds to the maximum. Okay? So second derivative tells you whether it's a minimum or maximum, and the first derivative tells you that it's either minimum or maximum. So like either extrema. So long story short, then this guy is gone because we are we are doing the Taylor series expansion in the point of the minimum, right? So we decided to do that in this derivation, and then the first non-trivial part is a quadratic one, right? Because the linear part disappears since the first derivative is 0. Okay, so then if it's quadratic and the rest for now we are ignoring, because why would we ignore the rest? It turns out you can simply because it's like a particle. Imagine like a particle in the box situation again. As we talked in the particle in the box, we don't have a function outside of the box. Here, this sort of minimum is like a box, but the walls are not going to infinity right away. The walls are kind of raising, right? And because of that, eventually they will stop wave function to go out, right? So we will assume that the quadratic behavior near the minimum is adequate enough to represent the potential. And we'll talk about inadequacies of these approximations later. Okay. For now, this is the simplest yet the most reasonable from the physical point of view approximation for the wave, well, to solve for the wave function, but we're solving this by approximating the potential. Okay, so we're approximating the potential to quadratic function, and this is how we end up with a problem that is called harmonic oscillator problem. Okay, harmonic comes from the quadratic, so that's another way to say quadratic essentially. Any questions about this derivation? Because this is how we end up with our next big model system after particle in the box, right? So with the particle in the box problem, we had a second derivative and we had no potential. Potential was just essentially the box was like this. Potential was 0 inside the box. Outside the box, there was nothing. Well, it was infinite, so there was no function outside the box. But in this case, we have quadratic potential. And now we are considering how can we solve this, right? So that's the idea. Okay. So this is a differential equation. In one dimension, we will talk about how do we deal with more dimensions when we need to consider diatomics, let's say, because every nucleus will have a coordinate. We need to get rid of some of them. But for now, the simplest problem you could formulate with the quadratic behavior of the potential is this harmonic oscillator equation 10. Okay, so if no further questions, we'll move on to the solution. All right, before we do the solution of this problem, it's a difficult problem. At least if somebody knows how to solve it, let me know. Maybe it's trivial for some, but in general, it's not. So let's slowly simplify the problem. So the first simplification is we change the coordinate system so that there are some constants which will be combined. Right now we have this h bar squared divided by 2m, and then the k. This is, what is k is exactly essentially coming from the second derivative of energy with respect to the nuclear coordinate, right? And in the case of parabola, what the k is well, ax squared, a is a k divided by 2, right? So it's a curvature. All right, so if we change the coordinates like this, we introduce the coordinate q, which is scaled with the square root of mass coordinate x, right? So we have this, and the x square is this. So all these are relatively trivial transformations after you define this coordinate q dependence. Then the momentum is a little bit less trivial. So we want the momentum to go from the momentum with respect to x coordinate to the momentum that with respect to the q coordinate. Well, they are both rectilinear coordinates, so they're just scaled. One is scale of another. So you use the chain rule, right? So derivative with respect to q is just takes the m out with the square root because it's still first derivative. And we have this definition of the connection between the old momentum and the new momentum, right? More than that, the momentum before px squared divided by 2m turns into nice pq squared divided by 2. So m is gone because it gets absorbed into the coordinate. and the total Hamiltonian looks like this. So now we have only one constant that is of importance, omega, and that is some square root of ratio between the rigidity, the K, and the mass, right? So the K is the curvature. So in a sense, here K is A multiplied by 2, probably because we had the kx squared divided by 2 as a parabola relation, right? So the higher the K, the faster the growth of the energy. The smaller the K, closer we are to a free particle. Okay, so that's the idea. That's the direction of K goes up. All right, so and then we have the same relation for the frequency, omega. So the higher the frequency, then the kind of the steeper the parabola. But it also has a mass effect, which we'll talk as well. How the mass, it's all in one place now, which is why we did all these transformations, because we have now momentum and the coordinate and just one constant, omega. All right, so then after this simplification, there are two common ways to solve this problem still, since it's a still second order derivative, and then there is also potential that is quadratic. So there is a so-called solution with series, and in a coordinate space, it's more complicated, and there is an appendix in this document I'll post, which you can take a look, and there is a detailed explanation of that solution. Now, what we will be doing is the second way. It's called algebraic solution using ladder operators. And this is simpler. It shows the power of algebra over calculus in this case, although it ends with using the calculus just for a simple problem. All right, so what are these ladder operators? We introduced them. By the way, it turns out that these operators could be introduced to solve the particle in the box as well, but there the direct solution is simpler, meaning through just doing the calculus, because it's the potential is kind of trivial in the particle in the box, and that's why it's easier to work with the second derivative directly. Okay, so what is this? What are these operators? So it turns out they are some linear combinations of position and momentum. Okay, so you could see that they look somewhat complicated, maybe if you see them for the first time, and you may wonder in general why and how did people come up with them. Okay, so why is it natural to construct them? And it is related to one simple idea. Let's for a moment not worry about how they look, but the simple algebraic idea is the following. Imagine if we have a Hamiltonian, right? So we're interested in solving for the Hamiltonian. And if we have, in quantum mechanics, what makes things simple? If we have a symmetry operator, which commutes with Hamiltonian, right? So if there is a symmetry operator, it's the operator that commutes with the Hamiltonian. So then if it's a simple operator, we know when the two operators commute, they share eigenstates. So you could look for eigenstates of the symmetry operator, and that helps you to find the Hamiltonian eigenstates because they share, right? Now, this is great, the use of symmetries, and in principle can be done, but it's limited. There's just not many symmetries that could be used. It turns out that there is another interesting relation, which is, imagine you have an operator H, right, as before, but now you are looking for the operator, let's call it O, where the commutator with the Hamiltonian gives you back some constant multiplied by the operator. Okay, so it's almost like a next best thing. It turns out that this relation is even more useful sometimes than the previous one, right? So even though operator H doesn't commute with O, but it gives back this operator O with some constant. And you may wonder, okay, well, what do I do with this, right? So how is this useful? It turns out that it's easy to show the following thing. Imagine somebody says, okay, I have one solution for time-independent Schrodinger equation, right? So H psi equals E psi. Then what we can show is that O psi is also a solution, but it is a solution with a different eigenvalue. Okay, so it is a solution with a eigenvalue that is essentially alpha plus E O psi, right? So if alpha is positive, that means we can generate excited states, right? So if you start with the ground state, then we can create excited state. Okay, so that is the use of this expression, because it is powerful, because if you find such operator O, it can create from the ground state excited states. And you may say, all right, wait a minute, but somebody needs to give me a ground state. And I say, imagine you have a ground state. We'll get to that, right? So just for a moment, enjoy the power, right? So enjoy the fact that you before needed to solve all this for all these eigenvalues. Well, this operator expression, but now if somebody gives you one solution, you could get all the others. Okay, so that's the big advantage. And now let's see, what is this O operator? You could show that in the case of harmonic oscillator, if you look at the common candidates, let's say X or P. By the way, before we get there, I didn't show you how this is true, right? I don't wanna make you believe that this is true without showing. So to show this is actually quite easy. What you do is you take the operator HO minus OH, that's the commutator, right? So you apply it to state psi, that is the original one. And so then we can write, well, if H meets psi, it gives you minus OE psi, right? Because the psi is an eigenfunction. And when this happens, HO psi, so this is the result. For now, we don't know what to do with, right? But then on the other hand, all this is the same as alpha O psi, because we have the right-hand side of this expression. It's I alpha O psi, and then we could write simply H O psi equals to alpha plus E O psi. And that's the relation I showed like before. So as you could see, it's just the two lines that could confirm this. Okay. All right. So now, how do we find O? What is O? And to find O, you look for common candidates like H with X. What does it give? It turns out you could just do the commutator. I'll save you the time. It's proportional to P. Okay, you could do it at home. By the way, could be on exam. commutator with H with X, you should be able to find it, right? So it was in the midterm, how to do the commutators. All right, then you do the H. As you could see, H with X in this case is some constant times P. Not good, right? Because we would like some constant times X again. Doesn't happen. So then you do H with P and you find, oh, that is proportional to X. Again, not something great, right? So we would like something like alpha or beta, whatever constant, multiplied by P again, right? So, but from this could tell you that, okay, you're pretty close. If you take one operator commute of H, you get another one. And you get the other one, you get the first one. So what's the solution? Well, you take the linear combination of two, right? So you take the linear combination, and that's exactly what these B and B daggers do. They are aiming at getting to this expression, HO equals alpha O. So they are aiming to be these operators that if you give them the eigenfunction, they will produce another eigenfunction. All right, and that's why they have this form. They have the form that linear combination of Q and P, right, or position and momentum, is the kind of this is like a big idea. Now we will see how on the detailed level it works. Okay. So with details, now we could write this BB dagger operator, and we could check that if Q and P are not commuting, then BB dagger also not commuting. They commute, and commutator is 1. Okay, fine. That's all good. Now we could also write down the H that we obtain in terms of B and B dagger. Why would we do that? Because we want to confirm that if H is written in terms of B and B dagger, we could rewrite like, okay, what's the commutation relation of H with one of them, right? So we write the Q as a sum of B plus B dagger and P as a difference. Okay, fine. So now it turns out if you do the algebra, it's relatively simple. Like you square the momentum, you square the position, and you get this nice, really nice expression for the Hamiltonian. B dagger B plus 1/2 multiplied by the omega. So then we could say, oh, this B dagger B is operator N. That's the only operator inside the H. And you will see in a moment why we call it N. Right? So, but that's the only thing that is non-trivial. And now we could see that why B, B dagger are called lowering and rising operators. Because, again, turns out that if you look at the H, B, let's say, commutator, it's the same as, well, in H we have omega n operator and the constant, right? The constant commutes with everything, right? So that's why the commutator of H with B is the same as a commutator here, as the omega is also constant. This is a commutator of N with B times frequency, omega, right? So this is the most important commutator, N with B, and then N with B dagger. And we could see that these commutators exactly what we want. So this is sort of the relations that that show that even, yeah, I guess if you do the commutator B dagger B with B, so it's easy to show that it's alpha B essentially, right? How do I show that? Well, B commutes with itself, but then the B dagger B commutator is -1, right? So because B dagger is 1, right? So that's -1. So then the B operator and B dagger, they are raising and lowering, or they increasing or decreasing the eigenvalues of the functions for the n operator, right? So if n had an eigenfunction psi, then if you apply B dagger first, then you could see through this algebra using the what's the algebra is really well, we have this B dagger, right? So then it's convenient to so to move B through B dagger. Why? Because we want to obtain the n again, and that adds the commutator, and the commutator is 1 here. So long story short, you sort of shows that this shows that n B dagger psi is n plus 1 B dagger psi. All right. Or another way to say this, what would be, is that the B dagger essentially is increasing the eigenvalue from n to n plus 1. Okay. Any questions? Do you follow? Right. So what this is doing is essentially introducing operators that increases the eigenvalue, or as we could see that actually B reduces the eigenvalue by the same logic. That's what it's doing. Okay. Yeah. Okay. Yeah. So that was explained here. It will help us to solve, and because the solution of the Schrödinger equation is to find eigenvalues and eigenfunctions, right? Now, there is a potentially infinite, and in the case of harmonic oscillator, there's also infinite number of solutions, right? Now, what is logic with the commutator relations? If you find an operator that doesn't commute with Hamiltonian, but the commutator of the Hamiltonian gives back the same operator times constant, that's a magical operator, because what it does, you give that operator a function, it can create new eigenfunctions. Okay, so that's why it's the goal. It's like you found gold, essentially, right? That's why we want raise and lowering, because they can create more eigenfunctions from a single eigenfunction. Now, if you are pragmatic, or you kind of down to earth, you say, all right, but I still need this one function that to start the process, right? So how do I get that? And that is explained here. Essentially, it explained here. The one important thing is just to summarize. We have B and B dagger, and they are raising and lowering operators for n, and n, our h is omega n plus 1/2, right? So if we find a function for n psi, then that function automatically will be an eigenfunction for psi, for h as well, because of this relation, you could see that all we need is, if we apply h to psi, then it would be omega n plus 1/2 applied to psi, and that means we're applying omega n to psi plus omega divided by 2 to psi. That's a constant right away. This one is a constant because n operator acts on psi, gives you n frequency, right? So then the result is n plus 1/2 multiplied by omega psi. So that is illustration that if you find eigenfunction of n operator, it will also be an eigenfunction of h operator. Okay, so we could focus on finding eigenfunctions of n operator. Right, so then it will automatically lead to all the eigenfunctions of h operator, because h is just a linear combination of constant times n plus another constant. Okay, so then this relation is the most important for us, and B dagger operators, they are allowing you to go between the states of n operator, right? Because as we shown here, B applied to psi, that is an eigenfunction, gives you eigenfunction with the n minus 1, and B dagger applied to psi, it's n plus 1 eigenfunction, right? So this B dagger, they create more eigenfunctions from the functions that we have. Okay, there is this still problem that how do we start, right? So how do we start? That's the problem. The only problem that we now need to address, because once we address that problem, we know how to just apply in B dagger, get more states, more energies, right? So life is good. How do we do this? We look at this nice relation that is based on positivity of inner essentially what it all boils down to, you know that in quantum mechanics functions are vectors. Vectors, they always, you could define the length of the vector, like with the normal pointy arrows, you could define the length of the function. And that thing is it's always positive, right? So length is always positive. So now it turns out that if you take the function psi and apply n to it, so then you will get, interestingly, psi, B dagger B, psi, right? And this turns out to be the same as B applied to psi as a vector. Okay, so it's like a vector. And then B dagger psi is a vector that is essentially conjugation to the V vector. So what we have here is effectively vector times another times itself. Why is that? Because B dagger, sorry, it's not equal. Because B dagger and B are related with Hermitian conjugation. So if we have something like this, B dagger psi, so then we can write this as B applied to psi, B applied to psi, right? Because here it's directly, here it's because in order to apply this to the other side, you need to conjugate it. And we could see that the B and B dagger, look at this. If you do the, well, Hermitian conjugation, that just changes the sign in front of the I. That's the kind of conjugation, the complex conjugation, and both Q and P, they are Hermitian operators, so they're not changing. The only thing changes is the sign. And that's just to show that the B and B dagger are related with the Hermitian conjugation. So once you realize that, then it's the length of the vector B applied to psi, and it's always positive because it's a square. Well, it's a square of the length, right? So that's how we define length, is the inner product of vector with itself. That's why it's always going to be positive. Okay, positive or 0. Now, mathematicians like to say all eigenvalues are non-negative. That means they are positive or 0. So what that means, since we know that what the B, let's say, operator does, it reduces the eigenvalues of the n operator, but eigenvalue of n operator, they're all positive. That means if you take any function psi and apply the B, it will get you a function with a lower eigenvalue, and then lower again if you apply it again. But it cannot go forever because it stops at 0, right? So then we can formulate the following equation, that if B is applied to the bottom of that, say, spectrum of n operator, right? So spectrum of n goes from n equals 0 n equals 1, n equals 2, so on, right? So, sorry, I used small n for eigenvalues, right? So then if you have a state and the B operator will always lower it, but once it reaches the bottom of the spectrum, it cannot lower it further. So that's the equation that we can write now, that if we are at the lowest level, psi 0, then B applied to psi 0 gives you 0. It kills the so-called vacuum level. Now, this is a big achievement. Okay? This is a big achievement because it turns out if we go back to coordinates and momentum and differential equations, this equation is much simpler to solve than original one. Okay? So that's the whole idea, that we, with this algebraic relations, we found an equation that is easier to solve. So essentially, we found a state that is easier to solve for than for the entire spectrum. And then we found an operators that would get us from that state to any state we want. So we split the problem in two, and now we can solve it, right? So here there are some ideas that what are we going to do with solution. So this solution size 0 is just has a 0 n, right? So blah blah blah. That doesn't matter for now. We'll return to this later. But now, for the sake of just showing you the result, and we could talk about solutions later. This is the B operator in the coordinate representation. It has only first derivative, right? First derivative and coordinate applied to the function gives you 0. And this is very easy to solve. First order differential equation, separation of variables. Then you obtain the function that looks like Gaussian, right? So it's a function that has an exponential of q squared. This is a q, and this is a function psi 0q. Now there is a constant here, normalization, and you could find it by normalizing Gaussian. There's a Gaussian integral, which is a table integral, but it's easy to rederive, right? So, and that's the solution from which we can find all other solutions. And that's what we're going to be doing next time. Okay? Review the notes. Let me know if you have any questions. All right. Any questions? Okay. Think about them. We could talk next Monday.